On the 23rd of August 2023, India scripted history. With its Chandrayaan-3 mission, it became the fourth nation to land on the moon and the first on the lunar south pole. Within a short period of just a couple of weeks, the Vikram lander and the Pragyan rover made groundbreaking discoveries in the region of the moon that no nation had ever visited. However, the most intriguing event was recorded 3 days after Chandrayaan-3 landed on the moon. The mission's instrument for Lunar Seismic Activity, or ILSA, recorded a potential moonquake. Moonquakes, as the name suggests, are seismic tremors that occur on the moon. These lunar quakes are a fascinating phenomenon that has captured the interest of scientists and researchers for decades. The first moonquakes were detected during the Apollo missions in the early 1970s, and the tremors recorded by the Chandrayaan-3 mission could be the first moonquake recorded in over half a century. But why is the detection of these tremors so important for scientists? What other discoveries did the Chandrayaan-3 mission make on the south pole of the moon? Finally, and most importantly, what is that one significant thing that Chandrayaan-3, just like previous missions, has failed to find on the lunar surface? Where did Chandrayaan-3 land? To understand why the Chandrayaan-3 mission was so critical, it's important to know where exactly it landed on the moon. The moon has a near side and a far side. The near side refers to the portion of the moon that is visible from Earth. This side of the moon always faces our planet, and it is the side that humans have visited during various lunar missions. The far side of the moon is the side that is not visible from Earth. We can't see this side because the moon is tidally locked with our planet, meaning it rotates on its axis at the same rate it orbits Earth, taking approximately 27.3 days to complete both actions. Just one spacecraft has soft landed on the far side of the moon. It's China's Chang'e 4 mission. The point where Chandrayaan-3 landed, now called the Shiv Shakti point, lies about 600 km away from the south pole of the moon. The coordinates of the Shiv Shakti point are 69.3 degrees south and 32.3 degrees east, which means that the lander was still on the near side of the moon, which we can see from our planet. But these coordinates also posed 3 severe challenges to the mission. The first was the rough terrain. The South Pole is the most rugged and mountainous region of the moon, with large craters, deep trenches, and steep slopes. This makes it difficult to find a suitable landing site and to ensure a safe and controlled touchdown. The second was the perpetual darkness. Due to the moon's axial tilt and the deep craters near the South Pole, there are regions that receive very little sunlight. The sun hovers just above the horizon during daytime, and this limited sunlight makes it difficult to power solar panels and generate the necessary energy for a mission. Some areas near the South Pole have not received sunlight for more than 1 billion years. Finally, the temperatures at the South Pole can drop to as low as 230 degrees Celsius or 382 degrees Fahrenheit during the lunar night. This can damage electronic components and make it difficult to keep spacecraft warm. Chandrayaan-3 was designed to last 14 Earth days or 1 lunar daylight period. In these 2 weeks, the Indian mission has made some significant discoveries on the moon. Chandrayaan-3 results. Chandrayaan-3's trail of discoveries began with the lunar atmosphere. The moon has a very thin atmosphere known as an exosphere. It is so thin that it is almost considered a vacuum. The pressure of the lunar exosphere is around 0.3 nanopascals, which is about 1/trillionth of the pressure of Earth's atmosphere at sea level. Mixed on the upper edge of the exosphere is a tenuous secondary layer, the ionosphere, created by sunlight that energizes atoms in the exosphere. Instruments on board the Vikram lander made the first density and temperature measurements of the ionosphere. It was found that the 100-kilometer thick layer of electrically charged plasma surrounding the lunar surface near its south pole is relatively sparse. The plasma density lies somewhere between 5 million to 30 million electrons per cubic meter. Further, the density varies as the lunar day progresses. The density of an ionosphere plays a crucial role in radio communication. The higher the electron density, the longer radio signals take to travel through the ionosphere. So now, if the plasma is quite sparse, the potential delays would be minimal. Eventually, it would not pose a problem for transmission and navigation systems if humans were to inhabit the moon in the future. Furthermore, the lander made an interesting discovery just below the surface of the moon. A temperature probe containing 10 sensors reached 10 centimeters below the surface. A preliminary analysis of the data collected by this probe found that during the day, the temperature at the surface is around 60 degrees Celsius or 140 degrees Fahrenheit. But it dramatically drops as we go deeper into the surface. The temperature dips to about 10 degrees Celsius or 14 degrees Fahrenheit, just 8 centimeters below the lunar surface. That's a drop of around 70 degrees Celsius in just 8 centimeters. Such striking temperature variation indicates that the moon's topsoil is a powerful thermal insulator. This further adds to the idea that it can be used to build future habitats for astronauts to shield them from freezing conditions and harmful radiation on the moon. The next notable event occurred on the 26th of August, 3 days after the historic landing. The instrument for Lunar Seismic Activity detected a potential moonquake. Quakes on the moon can happen due to 3 main reasons. The first is an impact event when meteoroids or asteroids hit the moon, creating seismic waves. Then, the gravitational pull of the Earth and the Sun can create tidal forces that cause the moon to flex and deform, causing moonquakes. The third reason could be the extreme temperature variations on the surface of the moon, which can lead to thermal stress seismic events. Moonquakes are very different from earthquakes. They can last from a few seconds to as long as an hour. Also, they occur in clusters. This is unprecedented, and it suggests that something is happening inside the moon that is triggering these events. In recent years, scientists have come up with 2 potential explanations for these vibrations on the moon. One possibility is that the moon is shrinking. As the moon cools, it contracts, which puts stress on the interior. This stress can eventually lead to the formation of cracks and faults, which can then trigger moonquakes. Another possibility is that the moon is being heated up from the inside out. This could be caused by the decay of radioactive elements in the moon's core. If the moon is getting hotter, it could lead to melting and the formation of magma pockets, triggering moonquakes. Scientists are still trying to determine the origin of the seismic event that Chandrayaan-3 detected. It's the first quake detected in over 50 years and could contribute to studying the origin and the interior of the moon. The next big discovery came from the Pragyan rover's laser-induced breakdown spectrometer or LIBS. To analyze a substance, LIBS fires laser pulses at a sample, which then vaporizes the substance into a plasma. The instrument then picks up the light emitted from that plasma and analyzes the wavelengths to determine what elements lie within. LIBS detected aluminum, calcium, chromium, iron, manganese, oxygen, titanium, and silicon. But the element that caught everyone's attention was sulfur. One of the theories regarding the presence of water on the moon involves a process called cold trapping. In the extremely cold and shadowed regions of the moon's polar craters, temperatures can drop significantly. In these frigid environments, water vapor can migrate and become trapped in the form of water ice on the lunar surface. When water ice freezes, it can trap small amounts of other molecules, including sulfur. So high-energy radiation may have caused the breakdown of water ice, thereby releasing sulfur. Besides that, sulfur is a prime element associated with volcanic activity, making its presence essential for understanding the moon's geology and history. So far, no orbiter crossing over the moon's south pole has ever detected sulfur here, which makes this detection even more intriguing. Water ice. Despite all the groundbreaking discoveries that the Vikram lander and the Pragyan rover made on the moon, there's something important that the mission failed to find, and that is water ice. In 2008, the Moon Mineralogy Mapper or the M3 instrument aboard India's Chandrayaan-1 detected absorption features associated with hydroxyl or water-bearing molecules in the polar regions of the moon. The data collected by the mission was analyzed for over a decade. In 2018, a team of scientists used the instrument data to identify 3 signatures that definitively prove there is water ice at the surface of the moon. Yet, the Pragyan rover, like many other missions in the past, hasn't found direct evidence of water ice on the lunar surface. The detection of sulfur is indirect evidence that may have other implications as well. So the question is, where is the water ice that Chandrayaan-1 detected in 2008? There are 2 possible explanations to this question. The first is that the Pragyan rover was not at the right place at the right time. Besides confirming the presence of water ice, the 2018 study also found that ice deposits are patchily distributed. At the southern pole, most of the ice is concentrated at lunar craters, while the northern pole's ice is more widely but sparsely spread. So it's possible that Vikram landed at a place where there was simply no water ice present. The second explanation comes from one of the discoveries of Chandrayaan-3 itself. The chased payload aboard Vikram lander registered a sharp dip in the temperature just below the lunar surface. A dip of around 70 degrees Celsius or 126 degrees Fahrenheit just 8 centimeters below the surface suggests that the lunar soil is a poor conductor of heat. This means that the best place to look for water ice is not on the moon's surface but beneath it. Chandrayaan-3 had a planned mission duration of 2 weeks or 1 lunar daylight time. Any contact with the lander and the rover after that period would have been a bonus. The Indian Space Agency continued trying to re-establish contact after the lunar night ended, but there was no response. The mission was considered a success. It achieved its primary objective of making a soft landing on the moon, and it collected a lot of valuable data during its descent. The lunar South Pole is the most resourceful region of the moon, and India's Chandrayaan-3 has provided a treasure trove of data on the same. India is now working on Chandrayaan-4 in collaboration with Japan. The mission will comprise a lander and a rover that will extensively explore the lunar South Pole, aiming to make a direct observation of the elusive water ice on the moon. Astronomy is a beautiful subject, but sadly, it's not taught in most schools worldwide. So, if you want to learn about this subject at any level, you should check out this video's sponsor, Brilliant.org. Brilliant is the best way to learn math, physics, data science, and computer science interactively. All you need to do is set your course, and Brilliant will design a perfect learning path for you. So, whatever your skill level, Brilliant will customize content to fit your needs and let you solve at your own pace. Moreover, new lessons are added every month. In their astrophysics course, you can learn about how the universe works through meticulously designed lessons. This course beautifully takes you from the basics, such as lessons on gravity, matter, radiation, and the forces in nature, to advanced topics, such as supernovas, dark energy, black holes, and interstellar travel. Thanks to you for watching. On the 23rd of August 2023,